In this video, we consider the autoregressive distributed lag model, the ADL model. We look at the long-run multipliers and the long-run solution given by the steady state. We consider the ADL 1-1 model defined in the previous video. So yt equals a constant plus theta yt minus 1, phi 0 times xt plus phi 1 xt minus 1 plus a residual term epsilon t, which we assume either to be IID with constant mean of 0 and constant variance, or we expect it to have a conditional expectation given yt minus 1 xt and xt minus 1 equal to 0. Remember that this rules out feedback from yt to xt. Furthermore, we assume that xt is stationary and that the autoregressive parameter theta is numerically smaller than 1, so that the process yt is stationary. We are interested in the question, what is the effect of a permanent change in x on yt? So to answer this, we could start by taking expectation, just consider the unconditional expectation of yt, and then we take the unconditional expectation of the right hand side, and we get the constant term plus theta, unconditional expectation of yt minus 1 plus phi 0 expected value of xt plus phi 1 expected value of xt minus 1 plus the expected value of the residual term, which is 0. Under the assumption of stationarity, the expected value of yt is constant over time, so this is equal to the expected value of yt. Likewise, if xt is stationary, the expected value is constant, so the expected value of xt minus 1 equals the expected value of xt. So this is if xt and yt are stationary. Now this allows us to rearrange a bit, so we can write this as 1 minus theta, the expected value of yt, equal to the constant term plus, and now we have phi 0, the expected value of xt, plus phi 1, the expected value of xt. So this is phi 0 plus phi 1, expected value of xt. Finally, we isolate the expected value of yt, and we get that that equals the constant minus 1 divided by 1 minus theta plus phi 0 plus phi 1 divided by 1 minus theta, the expected value of xt. From this expression, we can see that the long-run multiplier, which is defined as the derivative of the expected value of yt given a change in the expected value xt, is equal to phi 0 plus phi 1 divided by 1 minus theta. So that's the coefficient here. We are differentiating with respect to the expected value of xt. So this tells us that if the level of xt changes by 1 unit, then the level of the expected value of yt changes by a coefficient of phi 0 plus phi 1 divided by 1 minus theta. So note that it depends on all the 3 parameters that we have in the ADL 1-1 model. Now we could define the autoregressive polynomial theta of L 1 minus theta L. We could define a similar polynomial for the effect of x. So phi of L is just phi 0 plus phi 1 L. And note that we could use this to write the long-run multiplier in the general case as phi of 1 divided by theta of 1. So the autoregressive polynomial evaluated in 1, and likewise the polynomial for x, phi, evaluated in the coefficient 1. So this was the long-run multiplier, stating that a permanent change in x implies a permanent change in y of a size of phi 0 plus phi 1 divided by 1 minus theta. Note that we could also have calculated this as the sum of each of the dynamic multipliers. So multiplier point t plus the multiplier in t plus 1 plus multiplier t plus 2 and so on. So if you add all these terms together, what you get is exactly the long-run multiplier that we have found here. Finally, we can use this to find a long-run solution defined as a steady state for the stationary variables, and that is given by yt equal to delta divided by 1 minus theta plus phi 0 plus phi 1, 1 minus theta xt. So this defines the long-run solution for yt given xt. We could also write this as mu plus beta xt like this. So that's all for now. Thanks for watching.